Good. So, well, first of all, welcome for new people that are joining us today in this seminar. Hopefully, this talk is not like not so boring that you feel that it's boring always. It's actually the seminar is pretty fun. There are like very cool things. So hopefully, with all the some proofs are very like technical, so don't get bored about that. And second, feel free to ask about terminology, things that maybe you don't remember or you haven't seen that before. Feel free to ask anytime, about terminology, about whatever you want related with the topic. And yeah, so well, the idea for today, so far we know what is a scheme, what is a scheme, and we know we have described some topological properties in the case of affine schemes. So what we will do today is kind of like see how to describe topological properties using coverings, affine coverings of those of schemes, and and try to define like some topological properties in terms of those on those coverings. So I will start with something we did last time. It was the affine communication lemma. So let me just state it again. So let X be a scheme. I'll just put it here. Then, and let P be a property satisfied by some affine open subsets of X such that the first condition is that if spec A inside of X, an affine piece inside of the scheme has P or satisfies P, then for all F in A, the localization spec AF inside X has P as well. The second condition is that if you can generate A with some finitely many elements, well, not the trivial, you can do it just with one, but if you can do it with any, like, there's any n elements that generates the ring, and spec A Fi inside X has P, then the whole spec A has P as well. When a property has these two conditions, we call it like locally affine. Let me just finish stating this. Then, if we can cover X by affine pieces, open affine pieces, where spec AI has P, or satisfies P for all I, then any affine open inside X satisfies P as well. Okay, so mainly this is saying this is a way in which you can compare different coverings. So if you want to state like properties, if you have one covering by affine pieces of X and you want to know some properties for any affine piece, if the property that you choose is satisfying this condition, so you are safe. So if you cover by no matter how many affine pieces and all of them have the property, then any affine would have the property as well. So we stated and proved it last time. Let me just say that in the proof, we used the fact that if spec A and spec B inside the scheme are open, we saw that we can write the intersection, we call V the intersection, we can cover the intersection by distinguished opens that are distinguished opens of both spec A and spec B, meaning that V, I can write it as a union of the distinguished opens. I will just put P to refer that I'm talking about the point P, where DFP is a distinguished open fine, distinguished open of both spec A and spec B. And I'm writing this because, well, just in a moment we will use this this fact that we showed last time. Good. So yeah, so what's the idea? In a scheme, when we want to define like topological properties, we have mainly two tools. The first one is you cover by affine pieces and you describe properties on the affine pieces, or you say that that all the stacks have some property. So those are like the two different like ways in which we can like verify properties, by affine pieces or stocks, and that's what we are going to do today. So some properties like reducedness, being Noetherian, and maybe two more new properties. We will just we have a version for affine schemes, and we will do it definitely locally, like having locally affine, having some property in those affines, or as we did, for example, for reducedness, that all the stocks should be reduced. So those are like the versions of the properties we're doing today. Okay, one more proposition that we will use. I'm not going to prove this one. Let A be a ring and generate by F1, Fn. A is reduced if and only if the localizations by these n elements are reduced. For all I9, A is Noetherian AFI is Noetherian for all I9. And the last one, let B be a ring. A is a finitely generated B algebra if and only if the localizations are this finitely generated B algebra for all I. There's no I in I. Just I1 to N. Any questions with terminology? Something to remember? What is do you remember what is B algebras? Reduced, Noetherian. Reduced, meaning that it has no non-zero nilpotent elements.
So,
what is an algebra?
No. What is an algebra? I know. What is B in this context? So
B is just a ring.
just some ring.
Some ring. Sorry. Yeah, it's some ring. So we will be A would be finite generated B algebra if and only if we just taste the property on those localizations.
Okay.
Good. Yeah, well, actually, this is a very just algebra statement. It's more general if you localize, but prime ideals, still you have the conditions. You can also prove it using the affine communication lemma by mainly doing from left to right using condition 1. And well, we saw that, for example, reducedness, in the affine case, spec A is reduced as a topological space if and only if A is reduced. So, no, I think I mean the sections are reduced. Just the definition of reduced as a scheme. Yeah. What is what?
What is a reduced scheme?
Is take the sections, and those are rings. So ask to those rings to be reduced. Yeah. Good. What else? Yeah. So you can. Well, actually, in Ravi Vakil's notes, you can just he gives you some hints to show this using that lemma, but we will just use it today. Good. So let's start with remark. I didn't want to call it a proposition, but okay. X is reduced. X scheme is reduced if and only if X can be covered by what? Yeah. So, yeah, it can be covered by reduced affine pieces, where spec AI, or I will just say AI, is reduced as a ring for Li. Good. So let's just see why is this. You can call it proposition if you want and prove. I'll just jump all that. So if it is reduced, it means that all the sections are reduced rings. So if you take a point, it would be in some, since it's a scheme, it is in some spec A for a sum ring. But no, I want to find the cover, right? I'm assuming it's reduced. I want to find a cover by reduced things, okay? Good. Yeah, so then the section is isomorphic to A, and well, spec the sections are reduced, so we're done. Because then actually we can cover by this for every point. We can cover X by all of these spec A's, and all of them are reduced. And in the other way, here we can use the version of reduced by saying on the stacks are reduced. So again, take a point, and now you have the covering. So the point would be in some spec AI for some I. That one is reduced. So if we look at the stack at the point, it's the same as looking at, actually, I think we noted the other way. I don't know. So it would be spec AI at the point, but the point inside of spec A corresponds to a prime ideal. We note it this way to say we're thinking on the point that comes from a prime ideal. Prime